Swayam Prabha. Digital India. Educated India.
Let's continue. So we're going to look at constraint handling, again the very similar way as we've done for the single objective constraint handling. Remember, we had this parameter less, and you did the first question on home assignment 2, right? How to assign a fitness with the constraints are present. Very similar thing we do here. So let's say that I've got these 6 points I put in the objective space. So this is the objective space F1, F2. And let's not consider the constraint first. So the entire thing here is feasible. There is no constraint. So I've got these 6 points, and if I want to classify them according to non-dominated fronts, again you see 3, 1 and 5 will belong to the class 1, right? Because there is nothing, no other point is in the third quadrant of each of them. Where is the other one? Here. But then if you temporarily discount, then 2 and 6 comes out to the second class, and then 4 is the third class, right? So that's how we classify them if there was no constraint. Now let's say I've got a constraint that comes in this way on the objective space. Usually the constraints are defined in the variable space, but when you map it, usually they are not very smooth, but it can be, if you have everything continuous, then you'll have a smooth line here as well. So this is the thing that says this part is not feasible, this part, only this part is feasible, right? So this green part is feasible. So what shall we do now to this classification? Because the selection will be based on, have you seen in the non-dominated, by the way, where is the selection in the NSGA2? Let's go back. Where is the selection operator? Yeah, how do we get the QT? So I didn't probably go into the detail. I said we do selection, tournament selection, crossover and mutation, and I get this thing. So how do I do tournament selection? So I pick any 2 of them. First I shuffle, right? You remember tournament selection, and I pick the first 2, and there we have single objectives, right? And I decide which one is better. Here, how do I do tournament selection? You see, first thing I'm doing, I'm not doing tournament selection. So when I do tournament selection here to get this, I need some kind of a way of saying this is better than that, right? So every member here is coming from the previous generation here, right? So they are already classified as, is it belonging to class 1? These are all class 1, these are class 2, these are class 3. So I already know that. So here the tag is coming, either it's 1 or belonging to 2 or belonging to 3, I know that already. So if I pick 2 solutions, one is from class 1, other is from class 2, which one shall I select? Class 1, because that is the better class, okay? So clear, it's clear. What if I pick this one and another one here that's also belonging to the same class, because there could be multiple points in the same class. They are belonging to the same class. Which one shall I select? Random? Random will not give you the distribution that I'm looking for. With each one of them, I also have the crowding distance. Remember the way I did crowding distance? Each one of them have a crowding distance. These ones are infinite, these ones are the size of the box. I have the crowding distance value. So each one of them has the crowding distance value. They are also passed over here. So now when I compare these 2, I first see which class it is. If one is at a better class, I select that. I don't look at the crowding distance at all. If they have the same class, then I look at the crowding distance. Which one shall I choose? Having higher crowding distance or smaller crowding distance? How did you pick here? Higher crowding distance is better because they are well distributed, right? So if this one has a higher crowding distance than that, then I'm going to pick this one out of the 2. So it's the tournament selection still, but now I have a hierarchical selection. First is based on class, second is based on crowding distance if I have the same class. Make sense? So all these members, okay, in the previous, so if this is generation T, in T minus 1, I already had this thing created. I've already computed the class, because you see these are all class 1, these are class 2, these are class 3, and for each of them I've also computed crowding distance. So these are already computed. The whole thing comes here, okay, and so I know this information already from the previous iteration, and now when I create my children, I need to apply tournament selection. I do this hierarchical tournament selection. Okay, it will come because see what happens is in the beginning when you're starting with the random points, usually there are very few points on class 1, lots of points on the other classes. Okay, so there are not many with class 1. So chances are that class 1 is competing with another class 1 is very small. But when you come towards the end, you've seen the simulation. I'll show you one more time. Usually there are lots of points on class 1 itself. So this is full of class 1. Now all you are doing is based on crowding distance. So that means if there is a gap, now one of those solutions will have a high crowding distance, and that is getting more emphasized so that I get a children created in the gap. So if I select the solution with near the gap, with crossover I am expecting a solution in the gap will be created. So all this is well thought of, right? And then this algorithm with the tournament selection picks up the right kind of solutions for crossover. Crossover mutation is as usual. Okay, so that's how we do, and here is the simulation as you see. Like right about here you see everything is in front 1, class 1, and so your whole that blue part is class 1. So you're basically picking 2 and deciding which one is going to win based on crowding distance. But early on again if you see early on there were in this problem there were still from the beginning, but for complex problems you have very few solutions in the first front in the early on. Okay, all right, so here so we got this thing, and now when I have the constraint I need to decide how do I do this classification. All right, so here is the small change I make. I call it constraint domination rather than just domination. So a solution I will constraint dominate solution J if these 3 conditions, one of them is satisfied. So I is feasible and J is not. So you pick 2 solutions to do whether one dominates the other. So in case of this I said 1 dominates 2, right, because 2 lies in the first quadrant of 1. So 2 gets dominated by 1. So 1 dominates 2. Here 1 will dominate 2 if 1 is feasible and 2 is not. That means if this is my 1 and this is my 2, then 4 dominates 2, although in the objective sense 2 dominates 4 because 4 lies in the first quadrant of 2. But now constraint is important. This is feasible and this is not. So I say 4 dominates 2 simply because 4 is feasible and 2 is not. Okay. Next condition, when both are infeasible, like 1 and 2 both are infeasible, with objective functions 1 dominates 2. But what did we do there? If it's infeasible, we don't even look into the function value. So we are not going to look at their location in the objective space. All you are going to look at is their constraint violation, which is kind of an idea of this much distance. This one will have small constraint violation, then 2, then 1. So 2 is going to be better than 1. So 2 is constraint dominate 1. So that's the second condition, very similar to the single objective one. And then if both are feasible, like 5 and 6 both are feasible, then 5 dominates 6 with the objective values. So that's why 5 is better than 6. So what happens then, if you now classify based on this, you see these cannot be in the first class, because one of the feasible solution will dominate. Okay, so 4 and 5 out of the 3 is going to be on the non-dominated front 1 with the constraint domination, this domination principle. So they will be on front 1 because 5 dominates 6, so 6 cannot be on the first front. Then comes the 6. After 6 comes 2 and then 1 and then 3, because unless the 1 is over here at the same constraint violation, they will be in the same class. Otherwise they will be in different classes. So unconstrained thing we had how many? 3 classes. Here we have 1, 2, 3, 4, 5 classes. But you see what's happening is that 1 is better than 2, 2 is better than 3, 3 is better than 4, like that. So there is a pressure for the points to go this direction, and there is a pressure for these to go in that direction. And here is my Pareto set, this one and this one. And you see we are having pressure from infeasible side to come towards the Pareto set, from feasible side to come towards the Pareto set. There is no parameter here. So this is how you have to think when you come up with a generic algorithm without any parameter, that what can I do so that the right kind of features is there for the algorithm. So this is again used by default. And here is the result with that. You see this problem is very complex because I have a nonlinear constraint. This is a sinusoid actually in a rotated form, and then another circle, and inside part is feasible, and you see the points are struggling to be on that Pareto front, and with iterations they keep adjusting these points. So it's a difficult, because if you are slightly below you are infeasible, if you are slightly above you are non-dominant, you are getting dominated. So it's a matter of time to find a point that will dominate you. So this kind of tussle goes on to be on that curve thing, and we've tested on many different problems. I'll show you this example because this was we did in I think in 2000 we did this. I was not a co-author, by the way. So this was the UIUC people, University of Illinois at Urbana-Champaign. I was visiting a year before, I think 2 years before of this. Are you seeing it or not? Yeah, no, it's coming. So there was a professor there in aerospace engineering, Coverston Carroll, and one of his students. They were trying to use this the interplanetary trajectory optimization, which eventually we ended up doing here with VSSC. But this was done in 2000, and I was not the co-author. So I was visiting them, and they were looking for a method to do multi-objective optimization for this. And they knew of NSGA. NSGA 2 wasn't still there. So they use NSGA. That's why I show this example from their paper. So they are sending a satellite from Earth, or rather a spacecraft from Earth to Mars. They did it on Earth to Jupiter, various other things in the paper. So I took just one example. So they were looking for a window when to launch. And so there are two objectives they had. One is how much time it will take to deliver the mass in Mars. Second objective was how much mass can I deliver. I always thought if you take more mass, then it will take maybe more time or something like that. But it turns out that there is a conflict. So if you want to minimize this and you want to maximize this, so here is the Pareto front they found using NSGA, the previous version of NSGA 2 with the parameter sigma, and I was helping them set the sigma correctly and all that. So let me explain, rather than the algorithm part, let me explain the results. And early on, this was in 2000, this was early for EMO. These kinds of applications kind of motivated people to pay attention to this. So let's take 44 solution, which is the minimum time solution, which is here. It takes about 1 year and few months to go from Earth to Mars, and here is the trajectory you can see. Okay, and you deliver about 700 kilos, slightly less than 700 kilos of mass at the destination planet. Fine. Then look at 73, another trade-off solutions, which is 73 here. Almost the same launch date or the same launch date, and you make one round around Sun, and then it takes little more than 2 years. One more year from here to there. That's why the path is longer. There's some coasting going on. Eventually, you deliver the mass. How much mass? It's about 170 kilos more than this one. So you wait 1 year, and you can deliver about 170-80 kilos more mass. Is it worth it? Who can decide? Can I decide? Can you decide? Probably not. It's probably the mission manager who has the goal of, is really that 180 kilos needed to be there? It could be 2 persons, or it could be on equipment 1 person. Is it absolutely necessary? Then you have to wait 1 more year. Okay. So these kinds of, so if you can find these alternate solutions, the mission managers who are not actually running the optimization, a subordinate is going to run this, go with these 4 or 5 solutions from it, go to the mission manager saying these are the solutions I found, pick one from it, and mission manager has his own goals in mind and all that, see how long they can wait, when they can deliver and all that, and decide based on this. This is the power of multi-objective optimization. One other thing I noticed, and that's why I picked this problem, is that let's look at 72. There is a small slope upward. Here is 72. It takes 3 years to get there. So 1 more year from here to there. How much more mass you take? It's exactly 3 kilos. that one I can even say, you can even say, hey, let's not wait one more year just to be able to take 3 kilos. This could be in the noise of calculating all of these, right? But there is a small slope up. So if I don't find all of them, how do I know that this is not the part to choose one solution from, because the trade-off is not good. If you just tell me some epsilon constraint, okay, and put this epsilon that you need to finish the mission before 2.5 years, you are probably going to get a solution here, and you don't see any of these other things, you probably went home thinking, I did a very good job optimizing, but you actually did a terrible job. If all these solutions are there, it says you should never be here, because there is not a good trade-off. That's second advantage of finding the Pareto set. So you know where to pick a solution from. This is the part where you should take solution, because there is a rapid change of trade-off here, right? You could have a 6-month solution, 1.5 year solution, you can have 1.25 years of solution and all that, but then the trade-off comes with the weight that you can take. So this kind of applications where you are finding alternate designs, people could see the trade-off and was very, very helpful in the early on. Okay, later on we did a lot of work with companies like Evolution. We're doing mine scheduling, and you're going to see the whole thing here. But yeah, this was like millions of variables to come up with a sequence of mining a region. These are 3-dimensional cubes that needs to be mined. There are a lot of constraints, like you cannot mine something below unless you mine the one on the top, right? You cannot mine something that is in an island, because you will not be able to put any equipment there. So all these things are there, and we came up with the whole software. They started at the back of a house with 2 persons, and then in 6 months, once the code is there, they moved to downtown Perth in Australia with 44 people working. Later on they were bought by this company called Maptech, which is a much bigger one. So they are a very rich company now. So it all started with this EMO algorithm consulting with me, just with one technical person, another one running around for money and projects. So it's a success story. There are many such success stories, not only with me but other people that are working in this field. Okay. What we do as a class project or anything that we deliver or put in the paper is this. Not many people do though. So we find with NSGA2 or any other method these circles for 2 objective minimization. We find this set that comes from the NSGA2 code. But NSGA2 code, like any other optimization algorithm, do not have a proof, right, that every time you run it's going to give you the Pareto set. No evolutionary method has that, no point-based method has that. If it's a random, if it's an arbitrary problem. If it's convex, linear, quadratic, yes, there is algorithms with proof, right? We've talked about it many times. So I took a problem, I applied some algorithm and I got some results. That doesn't mean they are optimal. And this is a question I always ask in defenses to the students. They say that this is the Pareto optimal solution. I said, can you prove it? Don't say otherwise that they are Pareto optimal, but we loosely use it. One of the ways we build confidence that these are good solutions, probably Pareto optimal, is apply several other optimizations. So circles are my NSGA2 and EMO run. Then what I do is we do a lot of epsilon constraints. So we put an epsilon here, okay, as a constraint on F1, minimize F2. I get a solution, I compute F1, F2 and I put it with NSGA2. I plot it with a diamond here. I do another epsilon, I got another diamond, another epsilon, another diamond. Like I do epsilon on this axis, I get each of them. Then I do individual minimization of cost, I get a solution. I do individual minimization of deflection, I get another solution. All of these individual single objective minimization, I do several of them and I put them on the same plot. If this happens, that all of them are falling on top of each other, that gives me a lot of confidence that these are probably, still I'm saying probably, but I have a very good chance, very good confidence that this could be the Pareto set, because not all of them can be wrong. I have done independent optimization with point based, population based, all are telling me the same place. Not all can be wrong. If you are wrong, this could have been here, okay, or here or somewhere. But if they fall on top of each other, very unlikely that all are wrong. Probably they are all right and telling the same thing. This still doesn't prove anything, but it just makes it more with more confidence. So this is something we learned here. We could do single objective epsilon constraint weighted sum and multi objective. We could do them and show them like this. So I recommend you to do this if you are using multi objective in your thesis. Okay, now let's talk about few things quickly. Visualization. How do we visualize? Okay, that's a big problem when you go more than 3 objectives. Very difficult to visualize. But let me show you with 3 objectives, but then you can all this can be extrapolated. So let's say this one is called the value path or parallel coordinate plot, where each of the line you see here is one solution. So I have 3 objectives, F1, F2 and F3. These are shown with these vertical bars, lines here, and this is the smallest value of F1, this is the largest value of F1, smallest of F2, largest of F2, and so on and so forth. So then you take a solution. This line here shows that this solution has the minimum F1 value and then worst F2 value and the minimum F3 value. That means this particular solution here is good for F1 and F3 but worse for F2. So when you are visualizing like this, you say, do I care more for F1, F3, F3 and not much on F2? Then maybe this is the one I would go for. Okay, but there is a reason why you put F2 in your algorithm in your problem. So you may be looking for something that is kind of intermediate, like maybe something that is here, and if I follow the line it is here, so good for F1 and F2 and not so bad for F3. So looking at this and looking at the axis, you can then figure out what's the combination of values I have here. You could do a bit more computation here to give you the trade-off and everything, but this is one way you visualize higher dimension. You don't visualize it very well, but then at least you see relatively where you are, because you want to be minimum F1, you want to be as below as possible, right? So picking a point from here, if the same one continue here, if the same one continue here, you have a good one. Ideally, ideal point would be like this, but you will never have that because I said ideal point never exists, right? So you will always have to go up and down and all that, and there will be crisscrossing that shows there is a trade-off, right? Something that is good here is not so good the other one, and the opposite, right? This one not many people use, but there are many techniques like this. So you are basically showing for solution 1 all the and 2 and 3 all the F1 values. So you have a relative idea of which one has a good value of F1, good value of F2, good value of F3, so on and so forth. So you can then objective wise look into them, because this could be in 10 to the 6, this could be in 10 to the minus 6, but they all can be scaled accordingly to see relatively which is good, which is bad, right? There are much better technique. This is called the scatter plot, where if there are 3 objectives, you do all 3 choose 2 plots, F1 with F2, F1 with F3 and F2 with F3. So this is enough to show. So this one is F1 on this axis, F2 on this axis, this one F3 and F1, and this guy will be F3, F2. So these are the 3 pairwise plots you see. Look at the trade-off and all that. If you have a competing algorithm, you can put them here and compare this with this, this with this, and this with this. You can compare and see which one has done better. Okay, otherwise one side is enough. This is another one called star coordinates. So if you have 3 objectives, you have this 120-degree line. This is the best one for F1, this is the worst one for F1, best one for F2, worst one for F2, and you basically mark those points based on your actual F1, F2 value, and you will end up getting a triangle. So ideally you want everything to be 0, but it's not possible. That's the ideal. So you'll always have a triangle. Now all you are looking for is smaller size triangle. The smaller the size, the better it is for all objectives. So sometimes they don't do these things, they just show the triangle. Like this is one solution, this one will be another solution, and this one is another solution. So of this is best because the smallest size, but because it's in this direction, you know that F2 is in this direction, so you know that F1, F3 is great, F2 is not so great. Okay, this is a very sophisticated method designed by this Russian guy called Alexander Lotov. What he does is, once you have the Pareto set, you give like few points from your EMO he creates lots of points intermediate. There is a way to do that. We talked about ASF, right? So if you take the mean of 2 consecutive points and use that as Z bar for the ASF method we talked about yesterday, and go and find the Pareto set. So then you take the mean of the 2 and then do it. So he has an automated way, parallel computing, he finds thousands of points like this quickly. So more optimization is done to find them. Once you have all of those points, now you can choose the top 3 objectives that you have in your problem. 2 of them you choose here, and third one is does with the contouring. Okay, all other objectives are put here. So you can take this bar and put it anywhere you feel like, and this changes. So you can get an idea of the most 2 important objectives that you have in mind, their trade-offs, and the third objective comes with the color. Okay, and all others you can fix to some value. That's why he needs so many points to do this kind of maps. And on Friday, Dipanshu and Dr. Amu is going to talk about ISOM, and that's another nice way we figured you could visualize high dimensional data. Okay. We also did another one called palette V's. So this was the value path or the parallel coordinate plot, very difficult to know the trade-off. So what we do is, if you have a Pareto front, like this is 8 dimensional problem, so 8 objective problem. Okay, one of these is called rad V's. What that is if you have, so 8 dimensions, we have an octagon, right? Okay, and then any point you have here will have 8 values, 8 different objective values. The idea is these are your anchor points on this octagon. You assume this point is connected with a spring to every one of them. Okay. The spring stiffness is inversely proportional to your F. So if this is 1, 2, 3, this one is inversely proportional to F1, inversely proportional to F2. So if you have a very small F, you have a very large stiffness. It's a very stiff spring. If you have very large F, that means not good, you have a soft spring. So now you apply physics and find out the equilibrium point when each of the springs are in equilibrium with the forces. What is the location? And this will always be inside, right? What is the location of that? So that kind of tells you an idea of these 8 dimensions, what it's doing to that puck in the middle. So these points you see, these are those locations in this octagon. Okay. Now why I have so many octagons? If you put all your Pareto points into one such thing, you get very crowded, you don't know what is what. So we said, I have a Pareto surface. When you have 8 dimensional, will be 7 dimensional Pareto surface. We identify the boundary ones first, all the boundary ones first. There is we have boundary search algorithm we have from the Pareto set, 8 dimension or any dimension you can do that. We identify them, put those points into this rad V's, and we have the top layer. Okay. Then we go to the next layer, this one, and do the second one, third one. Finally we have the core which is here. So this is functionally decomposed. Again you see these functional things, the Wright brothers I was talking about. So why is this important? Okay, again if you think of the decision making point of view, a decision maker will choose a point here or will be interested in a boundary point because it's such a point, it makes the objective trade-off in a way that on one side of it there is no solution exists. So this is kind of the extreme. He may be interested in knowing why is it extreme, what is this extreme point, but he may not choose from there, because when you are extreme, like let's look at 2 objective, this is the Pareto front, the boundary will be this and this. Would you be interested in choosing this one or that one for your solution? Because you'll have lots of points here, right? Would you choose this or that? Why would you choose? Because if you choose this is best for F2, totally ignoring F1. If you choose that one, it's best for F1, totally ignoring F2, and you will never do that. Then it's not a single multi-objective problem, it's a single objective problem. You will probably choose from here, right? So that means the core for 8 dimension. But you are still interested in knowing these because you know that that's the extreme you can go. These are the extreme values of F2, and maybe when a multiple objectives comes from multiple objectives extremes. So you're interested in them. So that's why we put them on top here. and the core is right there. So once it's decomposed like this functionally, decision maker can go and look into this one first, because any of these points here makes a very good trade-off. This is right in the middle at the core of the Pareto set. It's making a good trade-off about all the objectives. So this is most likely your place to choose. What more we do is we put some of these brown circles. This one is not properly done, but these circles, you see, this one is slightly smaller diameter than the other one. They vary with diameters. The diameter is in proportion to trade-off. So we defined a trade-off, like how much you sacrifice going to your neighbor versus how much do you gain. So if the dimension is small, means you don't have a good trade-off. If it's a big one, means you have a very good trade-off. So these ones are excellent trade-off solutions staying on the core. So if I am the decision maker, I'm going to go to this core and I'm going to look at these two solutions first and see if I like them. If not, I will try to see here. Now here you see some color coming. As it gets more and more towards red, you are getting closer and closer to the constraint boundary. So you may be careful in picking that. If your green, means you are really far away from the constraint. There is no problem being close to constraint. Okay. If I don't like any of them, then I move to the next level, which will be this one. Okay, this one here, and then I look for if there is any brown ones. If not, I go up like this. So this is a way we suggested functionally decomposing the high dimensional Pareto set and also marking the points in colors and sizes featuring of certain parts of the property of the points. This is, I think, the way to do. A lot of people follow visualization from data analytics literature, because data analytics also people do a lot of high dimensional data visualization, but our data is special. Our data has trade-off. Okay, you sacrifice in one objective to gain in another. So that kind of data, and we should have our own ways of showing them. This is something we figured out, but then I think there are more scope here to do stuff. Okay, that's all I'm going to say on the visualization methods. Other important thing is also performance metric. So remember, now we are comparing two sets. Okay, so you get one set of points by algorithm 1, your algorithm, and you use NSGA 2, which is like 12 years old, 13 years old, and let's say you got this. Which is better? Very difficult to say, because these are sets, and here NSGA 2s are better because this one dominates that, but here your method is better because it dominates NSGA 2. So which is better? It's difficult to say. In fact, these people, there is a group of researchers in 2003 came up with saying, oh, you need M metrics. You cannot have one metric. You have M metrics you compute, and then together these M metrics say something about which is better. They are very difficult to use. Theoretically they are fine. Again, I look at things functionally, being an engineer. So I look at what is the goal of multi-objective optimization. First goal is to converge. So I can have one metric that directly measures the convergence, how close I am to my known Pareto set, or between the two set, which one. I can actually take all the ones that are combining the two that are actually on non-dominated set, and then I compute the distance, okay, from that set, and then see which one has a smaller distance. So that has better converged. Then the other thing is the diversity measure. Second goal, I also have to have a good diversity, and I can come up with some metric for that. So there are lots of metrics like this. Again, I'm not going to go into the detail except couple of things. One is the IGD, the other I'm going to call as GD. So let's say this is a problem where I know where the Pareto front is. It's a test problem. I'm still developing my algorithm. I know where the goal is, where the Pareto front is. I'm checking if my algorithm has gone there and how it has distributed my points. So this black line is known to me, and I have created few points like these circles, black circles. I call them P star. This is the reference set. I know that. And these squares are my algorithm's performance. They found, let's say hypothetical, again they found their size need not be same. Okay, this one can be more points than the other one. So now GD, let's talk about that first. Generational distance is going to be the distance for every point of yours. I go and look into the circles and see which one is closest. Okay, I have another picture here, I think. GD, where is GD? Here, GD. Okay, I don't show it here, but let's go to that one and show. Okay, so GD is going to be for this one which is closest, maybe this one is closest, right? So I compute this distance, delta 1. For this point, this is closest, not that, not that. So this is my distance called as delta 2. For this point is 0. This point, this is the distance. This is the distance. That's it. Okay. So I have 1, 2, 3, 4, 5 because I have got 5 points. For each of my point, I compute the distance from the reference set and I take an average of that distance. So that tells me an idea of how well I have converged. It's nothing to do with the diversity. All these points can be just over here, but I'm computing the nearest one from the reference set, and so it doesn't say anything about distribution. It's only convergence. So that's called GD. Before you do that, you should normalize. Okay, any distance measure you should normalize based on the minimum maximum that I talked about, right? Okay. What is IGD then? IGD is inverse generational distance. You take the distance from the reference set to your set. GD, your set to the reference set. So I take this one, which is closest square for this circle. It's this one. So this is my one. What is closest for this one? It's the same one. So this is my distance. Closest for this one to my set, this one, this one, this one, this one, this one, this one. So now I have 1, 2, 3, 4, 5, 6, 7, 8 distances. I take an average of that. That's going to be different from the GD, right? Because now I have more points here, more distance. So if you've gotten only point here and there is a big gap here, all of these will make large distances. So your IGD is going to be very, very bad. So IGD kind of does both convergence and diversity as one metric. Because of that, this is the one that is used most often. Not GD, but IGD is most often used. There is a new one called IGD plus. Let me not go into that. That's a bit more complex with the geometry. But this kind of talks about both convergence and diversity. There is another, I'm not going to go into this one. This is also most popularly used. It's called hypervolume. What is it? Again, the same set of points that you found with square. Here is my Pareto set, but in the hypervolume, okay, one of the problem with IGD is that you need to know the Pareto set because the reference set needs to be known. Here, you don't need to know the reference set. Once you have these points, you come and choose a reference point. Usually, you take the highest one here and the lowest one here because you need to normalize anyway. This distance map to 0 and 1 and you go 1.1, 10% more. Okay. Here also the same thing, minimum maximum go 10%. Here it's more than 10%, but go there and you construct that point. That way you are basically going 10% more. There is a recent literature that says don't do 10%. This is an ad hoc. Do here 1 by the number of points. So if you have 1, 2, 3, 4, 5 points, you will do 0.2%. So when you are 0 to 1, then you just go to 1.2. 1 plus. So this is 1 plus 1 over n, 1 plus 1 over n. Okay, this reference point. Once you have done that, then you look at every point, how much area does it dominate? So it dominates the first quadrant. How much area does this dominate? Again the first quadrant. How much area does this on first quadrant? So like that you do every one of them and terminate it here. Don't go beyond this side or beyond that side, terminate it here and then take the common area. That's called the hypervolume. So now if your hypervolume is large, your points are more towards the Pareto set. In fact, there is a proof that said hypervolume is maximum when all your points are on the Pareto set. Because you see, if instead of this, if you had found on the Pareto set, you would have added this much hypervolume. By not being on the Pareto set, you have sacrificed this much area, right? If this point was here, you would have added this much area, right? So when you take two algorithms, two sets, compute for the same reference set, hypervolume 1, hypervolume 2. If hypervolume 1 is better, higher, bigger than hypervolume 2, then first one did better. There are some issues with that. I mean, the boundary, how much you set, it matters, the hypervolume value matters, but it's kind of agreed that we are going to present our results with hypervolume. And so any EMO paper, if you look at either IGD or the hypervolume is used to compare different algorithms. You know now how to compute. Two objective, very easy to compute, right? You can sort the points and add up these areas one by one, these areas, and you get your hypervolume. Can you think of for three objectives what's going to be? It will be very, very complex. So they have until about, I may be wrong here, but I think about 5 objectives. I don't know that Dipanshu knows. Have you found anything more than 5 that can do exact hypervolume computation? But there are sample based hypervolume calculation. What they do is, once you have this W, right, which is 1.1 plus 1 over n, 1 plus 1 over n, and this end is always 0, 0, 0. So you have a square. In case of 5 objectives, you have a hypercube of size 1, of 5-dimensional hypercube. You create lots of random points here, lots of points here. Then you see which points your Pareto set dominates. Not your Pareto set, your non-dominated set dominates. So all the points that are in this area will get dominated by your A, B, C, D, E, right? Count those numbers, divide by the total set of numbers you have. That gives you a proportion of what's the area here compared to this hypercube volume. Okay, so that gives you a rough idea of hypervolume. Now, when you go to 5, 10 objectives, you need to create lots of points to get any accurate estimate of hypervolume. But you know there are bias sampling methods. Do you know? You can create more points in the boundary here than here. So you can actually have bigger grids here, smaller grids as you go along here, even smaller grids, even smaller grids. So you can have lots of small grids here and create equal number of points on each grid, like they do in finite element, right? And now you see what proportion of points is there multiplied, you do a weighted area, and that gives you a much better estimate. So there are 2 PhD theses I know of completely on sampling based hypervolume, and they get accuracy like 3 decimal, 4 decimal, 5 decimal places of accuracy, just that more and more points you need to do. So these are statistical sampling theories you have to use, but this is another kind of area where people are spending time, because once you know how to accurately estimate hypervolume, you can actually have algorithms created with them. There is one algorithm called SMS-MOEA, multi-objective evolutionary algorithm. SMS stands for something I forget, but this is basically hypervolume based. Okay, that's the hypervolume. Now the last metric I'm going to talk about is attainment surface. So here our algorithms are stochastic, as you have realized. You run it once, you get a set of points, like maybe these points. These red points you got once you run your algorithm once to a problem. You run it again with a different initial population, maybe you are going to get these points. Yeah, these other ones, the dashed ones, right? Then you run it again, you get another set, slightly different from each other. There is a way, it's called attainment surface. So if you have set of points like this, which are trade-off, you actually identify the boundary that dominates the region. So this part is dominated by your point, and that's how we did this line here, right? This is called the attainment surface, because in higher dimensions you don't have line, you have surfaces. So in general it's called attainment surface. So basically from your points you can identify the boundary which demarcates the domination part and non-domination or not getting dominated part, right? So for one set of points you can plot that attainment surface, another you can plot another one, and that's why you see there are 3 runs there and 3 different things. Once you have plotted them, now you can go orthogonal. So you can basically go to minimum of any of these and here minimum of any of these and join them with a line and then go orthogonal to this line. Okay, but the idea is you go orthogonal to the line, or you can choose any line, and then you see where each of these attainment surfaces is intersecting this line. and you make the line straight. So let's say this is A, this is B, so you straight it, and you do, if you have 100 runs you made or 50 runs you made, there will be 50 places you are crossing. You do the frequency distribution. Do you see what I am doing? Along that line, and identify the 0th percentile, 100th percentile, 50th percentile based on the frequency 25 and 75 percentile. There is 5 points you can mark on this line. Okay. Now go to another line like this, repeat the process, another line like this, repeat the process, and now you come back and look at all the 50th percentile and simply join them with a line. That is done over here. Okay. On a real problem, the dark blue line is the 50th percentile line. What does this say? This says I made 50 runs, this is my median performance, because 50% of it is below. 50th percentile always means 50% is below, 50% is above. So 50% of the time I am good, and 50% of the time I can be worse than what this is showing. So this is what my algorithm has done. Then I can show you the 0th percentile, which is this bottom line that says I could never cross this line, because here are better, right? And maybe the actual Pareto front is here, and your algorithm could only do this. So you are saying I don't know where my actual Pareto front is, but what I have done that says this was the best I could do with all my 50 runs. Okay. And the top one is 100 percentile point, saying every time I was better than that line. So if I take that line, if you are really pessimistic, you show the 100% saying I am always better than this line. I have never got any point here. And 50th percent of the time I am here, 25, 75. Usually we show these three, 0, 50 and 100. Now, if for an algorithm all the three lines are very close to each other, that means what? You have very consistent performance. All your 50 runs that produce almost the same result. If you have this white thing here and white thing here, means this part sometimes I got good results, sometimes I did not get good results. So my algorithm has some issues on this part and that part. Here I have done a good job. So you can get this kind of ideas if you are discussing this for decision making, for example, and you are as part of the team sitting with the decision makers, and as they are going to this side and picking up a point, you say, wait a second, if you are really interested in that side, I need to go back and re-optimize, because I see here there are a lot of deviation. I am not sure that if you've got good results there. But if they are focusing here, you just keep quiet, because you know your algorithm did well. Okay. So there are all kinds of statistical part that people have done, and codes are available for these from internet. You can download and use. Okay. So what we talked about today is we talked about evolutionary way of finding Pareto set. We talked about the importance of convergence and diversity. Diversity can be in two spaces. NSGA2 does it in the objective space diversity, like SPA2 and other methods, PESA. We also talked about how to handle constraints. I showed you some examples and the importance of finding the Pareto set rather than one at a time, whether it's a convex, concave, it doesn't matter, because we are not using any weighted sum or anything. And then we talked about performance measure, and we also talked about visualization, some part of it. Okay.